Hello, everyone. My name is Fan Li. I'm from School of Engineering, University of Warwick. Welcome to today's presentation. As you can see from the title, it will be about MOSFET design and oxide reliability. So for the MOSFET design, I will briefly talk about the guidelines we adopted in deciding the key parameters, and then followed by a demonstration of the choice of the junction termination, which to achieve the desired breakdown voltage. And in terms of the oxide reliability study, I will go through the background testing rig and the chip fabrication. Testing method we applied include both medium and long-term analysis, which I will further describe in the following slides. And in the end, I will provide a summary to the above work. So first thing to do in our MOSFET design is to plot the unipolar limit graph using the impact ionization coefficients we found from literature. And this graph shows that the maximum blocking voltage we can achieve for a given drift layer doping and also the minimum thickness required. There are some literature data points on this graph, so we know that the plot is not far off the reality. And from this graph, we can see that to achieve the 650 volts target, we will need the drift layer have a doping below 1 in 16 and the thickness higher than 8 micron. So these two values will provide us the device drift region resistance, which is one part of the device total resistance. So apart from the drift region, another contributing factor which contributes significantly to the total resistance is a channel. It is mainly determined by two parameters, that is the channel length and the field effect mobility of the carriers within the channel when the device is conducting. So here we fix the channel length to 2 micron, since most literatures have this value when they fabricated their device. And as we can see from this graph, the device overall specific ohm resistance is improving with an increasing channel mobility. And again, we have some past work results here to verify the curve. And with the 3C growth technology improved this year, now we can expect a channel mobility value practically between 100 to 200. And this means the final device specific ohm resistance should sit somewhere between 4 to 5 milliohm centimeter square for a 2 micron channel length. So starting from here, then we move to the TCAD modeling. So one of the things worth mentioning is the junction termination design for power devices. So if we take this half cell as an example, with a drift doping of 5E15 and a thickness of 10 micron, ideally the avalanche breakdown in reverse bias will happen at 710 volts, as you can see here. And if the depletion assumed to be happening only vertically, so it's called one-dimensional case. But in reality, the depletion happens in lateral direction as well. So this will cause the electric field to crowd at the body corner, as you can see here. And this will lead to the device early breakdown. And in this case, only 230 volts can be achieved. And to prevent this crowding at this corner, we looked into various terminations, and among them, P-ring turns out to give the best performance. So P-ring is essentially a series of P-type doped deep junctions around the edge of the device active area. So if you have a circular device, and from the top view, the P-ring will be a bunch of concentric circles. And in this example, the P-ring widths are 1 micron, as well as the gap between all these rings. And this will add up to a total length of 60 microns. And with this termination, the device blocking ability has been greatly improved from 230 to 680, which is close to the ideal value. If we compare the more conventional single or double zone JTEs to the P-ring, the P-ring has the advantage of being less sensitive to the P-type junction dose variations. And this variation can be an issue for silicon carbide processing, because silicon carbide generally requires implantation and activation. And the disadvantage of the P-ring is that it usually requires very small features, such as here, 1 micron features, and it is more challenging in terms of photolithography work. And the zone JTE, such as a single zone JTE, their dimensions are usually in the tens of microns, so much easier to achieve. In current stage, we have finished the prototype device design in the TCAD, and we are finalizing the fabrication process. And we have already have the mask sets are ready, and the clean room work is about to start. So apart from the design and modeling work, we also looked into the actual fabrication of separate features on the MOSFET. So one of this is a MOS interface. Here we will mainly talk about the reliability study we performed on this topic. So the conventional theory about the oxide reliability is that when you apply a voltage to the gate terminal, electrons are injected to the gate oxide. And since there will always be defects or traps in real-life oxides, these defects will act as charging and discharging point, forming a conduction path for electrons to get through the oxide, and finally reaching the silicon dioxide and semiconductor interface. And at that interface, there is an energy barrier which will need to be overcome. And this barrier is caused by the band offset between the silicon dioxide and semiconductor. And the tunneling current will eventually lead to the oxide breakdown. So from this band diagram on the right, we can see that the offset between 3C and silicon dioxide is the largest comparing with 4H or even silicon. So it means there's a good potential for 3C to achieve a more reliable gate oxide. So to start with the process, the devices we used are the MOS capacitors fabricated in our own clean room. So we started from 4-inch wafers, and in the end, we have this 1 centimeter square dies. And on each die, we have 32 MOS capacitors. And each of these die was then soldered and wire bonded to a PCB, which has 32 leads connected to the testing circuit board, and independent power supplies for the testing circuit and for the gate bias. The real-time leakage current is amplified and fed into a PC using a DAQ unit. So we will be able to know when and which capacitor have failed. Only room temperature is available for now. So the first test we did on these MOS capacitors is to gradually increase the gate bias and check the cumulative failure rate every 1 hour. So it's called a V-ramp method. Immediately, we observed a quite obvious error dependence of these devices. Basically, the bigger devices, here the 200 and 400 micron ones, the bigger ones, they fail much more quickly than the 100 micron MOS capacitors. So actually very few of these bigger ones made it to 9 megavolts per centimeter. So it means the crystal defect density is still quite a concern here. And to continue, we only look at the smaller devices here, so the 100 micron ones. And a first look tells us there are at least 2 dominating mechanisms involved in the oxide failure. One at a relatively lower field, namely the crystal defects we mentioned before, and the other one showing up above 8.5 megavolts per centimeter, and from the literature, most likely to be tunneling or electron impact ionization in the oxide. So if we convert the bar graph into a curve with y-axis as a function of the failure rate f, and the x-axis, the applied gate voltage minus the targeting operating voltage, which we estimated to be 20 volts here, then we can get a curve like you see here on the right, which can be further fitted by an empirical equation here. And before doing that, we can look at the curve, and we can see that already there's a third mechanism appears. And since you can see that the slope of the third mechanism is considerably lower, smaller than 1 and 2, so it can't be an overlap of 1, 2, and more likely is that 1 and 2 are actually shadowed by 3. So nevertheless, if we look at the equation again, we can find out that when Vg equals Vuse, that is your assumed operation condition, the failure rate can be directly calculated from the A value. And from the fitting for both mechanism 1 dominated and 2 dominated regions, we can calculate the A values. And from that, we get the failure rates. So the results that are, so in the worst condition, when the MOS capacitors are still troubled by defects 1 and 3, then the failure rate is around 3,443 ppm, so parts per million. And if the defects, at least the mechanism 1 defects, those can be eliminated, then we can see the failure rate greatly improve to 40 ppm. So it can be a really huge improvement. And for comparison study, so we have a state-of-the-art 4H-link carbide MOSFET, which have a failure rate in the roughly same order, but we have to see that the testing condition is much harsher. So after this medium-term study, we went on to do some more time-consuming and time-dependent dielectric breakdown tests. So here we again only showing the results for the smaller devices, 100 microns. So these MOS capacitors were biased at a fixed gate voltage until all of them have failed. The tested conditions are 9, 8.5, 7.5, and 6 megavolts per centimeter. And the graph is a Weibull distribution of the results. So the slope of this curve is actually a quick indicator. Basically, a lower slope, lower beta value usually means more number of failure mechanisms exist. If we plot the beta value for the decreased gate bias, you can see that the beta value is decreased first, then increase again, which is in agreement with the previous observation. So anyway, the overall beta value is still quite low. The highest one is close to 1, which is still 10 times lower if you compare with the typical results for 4H now. So it is most likely due to what we have said, there are slow killers, which is shadowing in all the gate bias conditions. And the origin of this slow killer is quite difficult to trace now. Could be a combination of multiple factors such as processing-induced defects, operating-induced defects, or simply another type of material defects. And from the TDDB results, we can use the E model, so it's an electric field model. We can use the E model to estimate the MOS capacitor's lifetime. And these estimations are based on results above 7.5 megavolts per centimeter. So in this case, the mechanism 1, so which is other obvious crystal defects are neglected. And we can see that at room temperature, if we want to achieve a 10-year lifetime for our MOS capacitors, they have to be working below 4.5 megavolts per centimeter. And this is actually quite an okay value for us to make some prototype devices. If we further take the temperature into consideration, and then the maximum operation condition drops to 1.4 megawatts per centimeter. And these estimations are for our MOS capacitors only with very specific oxide area and thickness. If we want to compare it with a more matured 4H technology, and you can see here, which can achieve 10 years at 150 degrees C at 4.6 megawatts per centimeter, we have to admit, and the 3C technology still needs a bump up. Okay, so now I come to the summary. In the beginning of the presentation, I introduced the tools we used for the 650 volts 3C MOSFET design, and the device fabrication is now ongoing. And then we moved to the oxide reliability study, and the 1 hour bias test tells us that the crystal defect density is still quite a concern in terms of the thermally grown oxide and reliability of 3C. And more detailed analysis suggests that there are at least 3 mechanisms leading to the oxide failure. There are 2 fast killers dominating the low and high field respectively. And we have another slower one, which seems to be affecting in all conditions. And in the end, the failure rate and the lifetime estimations results are okay. Actually, quite encouraging for prototype devices, but needs to be improved for the technology to be commercially available. And that's it. Thank you. Thank you for listening.